Hello friends, welcome back. In this video friends, we shall be looking at how we can get the moment of inertia of a uniform circular disk of mass m and radius a about an axis through its center and perpendicular to the plane of the disk. So friends, stay tuned and please watch the video so that you can have a clear understanding on how you can come out with this particular solution. So friends, this question keeps coming up in the further mathematics examination, particularly for those who are writing the Cameroon GCE, and for those taking engineering courses, guys, you will always have questions like this on moment of inertia coming up in your exam. So friends, if you're new to this channel, don't forget to press the subscribe button and press the bell icon to get notified each time we upload new videos. So friends, please give the video a like because it does motivate us enough to keep producing more great content for you. Thank you very much, and let's dive straight into our video today. Awesome friends, awesome. As you can see friends, the question reads that we should find the moment of inertia of a uniform circular disk of mass m and radius a about an axis through its center and perpendicular to the plane of the disk. Great. So friends, let's have a picture on how this looks like. Let's have a picture of it. Let's say we have the radius of the disk. We can call that radius a. Then friends, we are going to subdivide this disk into concentric rings of thickness delta x and radius x squared. So we are going to divide this our disk such that we can produce so many rings, guys. And we know that to get the moment of inertia of a ring, all of us know how to get it right. It is so easy to get the moment of inertia of a ring. So if we can divide this our disk into smaller rings whose moment of inertia we can all get right. So let's go ahead to divide, guys. We are going to divide this our ring. It has a center which you can see. We are going to divide this our ring into concentric disk into concentric rings, into concentric rings whose moment of inertia we can all find. So friends, by so doing, we are going to see that the distance from the center of this our disk, because guys, the rings we are going to produce here are going to be concentric. Concentric rings are simply rings in which they both have a common center. Okay, you can see that the center of this our first ring is still at this point. Likewise, at the second is still at this point, and the center of this our entire disk, guys, is simply at the point marked. Great. So guys, we can call this x. Good. So like I said, guys, we'll subdivide the disk into concentric rings of thickness delta x and radius x. Guys, you notice that in this case we can easily get the moment of inertia of just a single ring and sum them up, okay, because we are going to partition this our disk into so many rings, guys, so many rings, because when we combine all those rings it can give us back our disk. So getting the moment of inertia of the individual rings that make up this disk and summing them up will give us the moment of inertia of this our disk. Great. So friends, if we have that so well, guys, we can therefore go to tell them that let sigma, in this case, okay, this is delta x, we can tell them that let our sigma in this case be the mass per unit area. Okay, previously we have been using lambda, right? Let's use a different symbol. Let's use sigma to be the mass per unit area. That therefore implies, guys, our sigma now is therefore going to be the mass is m, the area of each of these our circle of these our rings, guys, is simply going to be pi times radius squared. The radius in this case is simply going to what, guys? Simply going to be a. Okay, it's simply going to be a. That is the radius of this our disk from the center is going to be a. So we have it to be pi a squared. Great. That's what we have, guys. Then now for each of the rings, guys, the surface area of each of the rings, guys, is simply given as pi. Is being given as 2 pi radius squared, right? That's the surface area of each of our disk. But guys, our radius in this case is x. Okay, our radius of each of these our rings, guys, is given as what, x. Then now the thickness is simply going to be what, delta x. That's why we no longer have the surface area to be given as 2 pi radius squared, but we have it to be given as 2 pi x times the thickness which is delta x squared. We have that, guys. Then we can therefore see that the mass of this our ring now is therefore going to be guys, keep in mind that if we cross multiply, in this case we're going to have m times sigma times pi a squared, right? Good. So we have our sigma in this case now. Then friends, this is going to be the area, okay? Then now to get the mass, we simply take the area or the cross-sectional area, guys, times what, guys? Times the mass per unit length, times the mass per unit area. Sorry, we are going to have the mass of each of this ring. Okay, good. So now, guys, since we have the mass of the ring now, we can therefore go ahead now to find the moment of inertia of each of this ring about the center O. So we are going to say that IO, which is the moment of inertia about the center, which is going to be given as the mass times the distance squared. The distance is simply going to be the distance from the center of this our disk to the point, to the radius of the, in fact, friends, it is simply given as the mass of this our disk times the radius of the ring. Okay, the mass of the sphere, sorry, that is the ring, times the distance from the center of that our ring now till it touches the surface of the first ring. That is going to be the moment of inertia of the first ring. Like I said initially, guys, we are going to split the rings in such a way that they are going to be approximately the same size, such that when summing them up now, it simply gives us the moment of inertia of the entire disk. Wait, this is what we have, friends. Now, friends, now for the entire disk, for our whole disk, guys, we can simply sum up all the moment of inertias of the individual rings we are going to create here. That is what we are going to have now, the sum from 0 to a now, guys, of the moment of inertia of the individual rings that we are going to form. Okay, this is going to be 8. That's the sum. Then now, guys, at this point now, we are going to change now from this continuous function now to a discrete function. So we are going to have now the definite integral going from 0 to a of just what we have here, guys, which is 2 pi sigma. Then, friends, this our x squared will multiply with x. Here we have x cubed dx. This delta x now turns out to be dx. So, friends, if we integrate this, guys, so well now, but we can simply put our 2 pi and sigma outside since they are constants. Then we are going to have the definite integral going from 0 to a of x cubed dx. So, friends, integrating x cubed, we simply add 1 to the power and divide by the new power. So we are now going to have now 2 pi sigma. Then we are going to have 1 over 4 x to the power 4. The limits of integrations are going to be going from 0 and will be ending at a. Good, that's what we have. Then, friends, plugging in the limit, we are going to have 2 pi times sigma 1 over 4 x. Put a, we have a squared. When we put 0, guys, everything gives 0. That's what we have. But, friends, keep in mind that our sigma is given as what? M over pi a squared. So if we plug in everything, guys, we are going to have 2 pi outside. Sigma is m over 4 over pi a squared times 1/4 a raised to the power 4. Simplifying everything, guys, gives us our answer to be 1/2 ma squared. Great. That's the moment of inertia, guys, of our disk of radius a and the mass m. Great. So, friends, you could still be asked to get the moment of inertia of a disk of mass 2m and radius 2a and so on, guys. You're going to substitute everything, okay? Just make everything, just substitute everything and put it into this our formula. You're going to have the same answer. Great. So, friends, thank you very much for watching the video. Thank you very much. It actually tells me that you actually found the video useful. Thank you so much. And guys, please like the video if you found it so useful, and put your comments in the comment section down below. Put your worries. If you have any difficulty, I'm going to attend to you as soon as possible. Thank you so much, friends, and have a blessed